Hello, welcome back to EE for Everyone and part 1 of the Plant Life project. The project that I'm going to share with you involves designing PCBs, switch mode power supplies, an enclosure, voltage regulation, and current regulation. In an ideal world, I would like to explain how all of these parts of the project work in enough detail that a beginner could understand what's going on and replicate it themselves. I filmed a few episodes like this. They were way too long, lacked focus, and ended up being more confusing than helpful. For example, when I tried to break down a switch mode power supply to the level where we discussed every component involved and how they fundamentally operated, it was an incredible quantity of information to capture or absorb in one sitting. Therefore, I've decided to reframe how we're going to discuss this project to limit the scope of each episode. We will be discussing and analyzing this design from a more intermediate perspective, where if a person had a basic level of understanding about how the components work, hopefully they will learn more about whatever topic we're discussing. That said, I really want to foster a strong culture of mentorship to highly motivated young people, and my ultimate goal of explaining how electronics work to beginners to jumpstart their learning and show practical examples of how math applies to the world around us hasn't changed. I've queued up a lot of video ideas that focus in on particular components, technologies, or circuit analysis methods. Throughout this series, if you see something that seems glossed over or you're interested in learning more about, let me know in the comments and I'll do my best to follow up. Now I think that's enough of my rambling. Let's kick off this series by discussing the design intent, problem statement, or the reason why I did this project. Where I live, our winters tend to be very cloudy, and the days are short for those who enjoy keeping plants that like lots of direct sunlight. These plants often wither during these months. By measuring the quantity of sunlight during the day and compensating for the day-to-day variability in the natural sunlight with additional light, the withering effect of winter can be eliminated. No ordinary light bulb will solve my problem though. This light isn't going to be used in a greenhouse, but in a home. Now many grow lights offer plenty of light, but only at 1 or 2 frequencies, and that doesn't look very good. One of our objectives here is to produce a color that looks closer to white for the human eye. This will prevent the typical pinkish purple glow of more typical grow lights. In order to do this, we will use a few different LEDs to create a swath of wavelengths that will approximate sunlight both for the plant and for a human observer. So our primary objective has been defined. We're going to build a replacement sun. Okay, let's slap some LEDs on a PCB, crank the brightness to 11, and photosynthesis will happen. Well, maybe, but that isn't precise enough for me. Plants not only need light, they also need some time without sunlight to finish the photosynthesis process. Some plants are very sensitive to this, others are not. But this plant light should be able to accommodate both types of plants, in my opinion. The complexity doesn't stop there, though. Some plants don't require direct sunlight, or could even be harmed by direct sunlight. By controlling not only the time plants are exposed to the sun, as well as the intensity of the sun delivered, our plant light will be able to keep a variety of plants happy. All the way from plants requiring direct sunlight for as many hours as possible, to plants requiring indirect sunlight for 3 hours a day. I don't know about you, but I'm often at work, not at home to turn my lights on and off. While we're at it, let's integrate a real-time clock into this light so it can track the current time and turn itself on and off. Hey, just by discussing some of what we want this plant to do, I think that there are some requirements here. Let's create some requirements, and that'll make it easier to know when we've finished designing the plant light. Once all of our requirements are met, our work is done. So, our requirements are as follows. We want to create an effective sunlight replacement for plants. This light must be bright enough to simulate direct sunlight. It must also be dim enough to simulate indirect sunlight. This light must be able to measure how many hours of natural sunlight there were. It must also be able to turn itself off after a certain number of sunlight hours has been achieved. This light must be able to turn itself on and off at a set time. Finally, This light must be small and attractive enough that it can be displayed in a living room without failing the wife approval test. That all sounds great, and this sounds like a plant light to me, but there's a small issue with a couple of those requirements. Specifically, how bright is bright enough to simulate direct sunlight? How big of an area must this light intensity be achieved? How consistent does the presence of the different wavelengths required need to be across this area? This requirement isn't specific enough to verify without further research, and diving into this project without defining this requirement properly could lead to creating a plant light that does not address our primary objective. The other requirement, dim enough to simulate indirect sunlight, is also a bit vague. However, if we can dim the light arbitrarily from 0 to 100% brightness, somewhere between off and full sunlight will satisfy this requirement. So now it's time to build a plant light, right? Well, we still have some requirements to hammer out because there are still some unanswered questions. Specifically, how many years should this plant light be able to run before failure? How should the settings for the plant light be updated? What should the user interface look like? What wavelengths of light are required to simulate sunlight sufficiently? Let's start on that last part first, with a photosynthesis overview. The overall reaction is as follows. Light plus carbon dioxide plus water creates a sugar and oxygen. There are two halves of the photosynthesis process. First, the light-dependent part, which takes the left-hand side reactants and creates intermediate products. Light excites the photosystems and causes them to donate electrons that kick off the reactions. Having light at the appropriate energies, or wavelengths, to excite the photosystems is more important than the absolute quantity of photons, or the brightness. Then, the light-independent reactions take those intermediate products and result in the right-hand side final products. The light required for light-dependent photosynthesis is dependent on the energy levels required for the different photosystems we need to excite. Photosystem 1 absorbs light using a molecule called P700, which requires 700 nanometer light. Photosystem 2 absorbs light using a molecule called P680, which requires 680 nanometer light. Different plants require different wavelengths of light, but it's important to cover a large portion of the visible spectrum where plants absorb the most energy. Therefore, these wavelengths were matched closely as feasible, and other colors were added in as well. The two wavelengths we specifically chose for the two photosystems calls for an infrared and red light. However, we will add in green and blue light along with some white LEDs to provide some intensity at nearly every visible wavelength. Here is a graph showing where different plants absorb the most light and how this aligns to the wavelengths of the LEDs that were chosen. We chose an IR LED with 720 nanometers, red with around 625, red with near 530 nanometers, blue with 470, and white, which is rated at 300K. Hopefully these LEDs will sufficiently replicate sunlight, and we'll talk about defining the remaining untestable requirements in future parts of the project video series. Let's talk about the tools we'll be using to create and test this lamp. We'll be using KiCad for schematic capture, layout, and design rule checking to prevent mistakes when implementing this design. We will use my soldering station, which is static controlled and features hot air and traditional soldering station to assemble the plant light. We'll be using an oscilloscope, multimeter, and lux meter to measure the performance of our plant light. Lastly, we will use Fusion 360 to model parts of the enclosure, including a heatsink mount with adjustable mounting pressure, the enclosure that will hold the plant light, and some brackets and spacers that will simplify assembly of the light. We'll be using my 3D printer to print out those parts that are modeled in Fusion 360. As you can probably tell, this is going to be a large project that requires a lot of effort. I'm really excited about sharing the rest of this project with you, and I hope that you learn a lot about electronics while we discuss it. That's all the time we have for this video, but we'll see each other again. For now, I hope that you learned something great today, and I hope to see you again soon. Bye!